Sorry, should I repeat? No, well, let's repeat briefly. Значит, we discuss kinds of hydraulic fluids. According to domestic practice, we have 4 kinds of hydraulic fluids. AMG10 is a rather old hydraulic fluid, petroleum-based, and so it's flammable. So it was used for a lot of years after Second World War, almost in all kinds of Soviet, Russian, Ukrainian aircraft, both civil, military, helicopters, airplanes. Only one disadvantage of this fluid is flammability. And it's still used in some obsolete models of aircraft. Now in modern aircraft, it is not used. 750 it's a hydraulic fluid which was produced from the mix of polysiloxane fluid and organic ether with some additives. The main its advantage is high thermal stability. It means it could be used up to higher temperature. So it is intended for supersonic aviation, for real supersonic aviation, such airplanes as Mikoyan 25, which can fly at high supersonic speed, about 3,000 km per hour for a long time, when actual temperature of the aircraft exceeds 150 degrees of centigrade and approaches to 200 degrees of centigrade. So it's of course expensive, it's not so convenient to use such fluid, but for these conditions it's only way. And these two fluids, НГЖ-4У и НГЖ-5У, it's Russian abbreviation, негорючая гидрожидкость with different names, улучшенная, so it's non-flammable fluid, and it's improved. So it's synthetic explosion and fire-safe fluid on the base of phosphate ester. It has a lot of additives to improve viscosity, anti-hydraulic, anti-oxidative, anti-corrosion, and anti-erosion properties. So main advantage is it is non-flammable. So it is used in modern civil aviation, domestic, Russian, Ukrainian. But it has two disadvantages. First, it is plasticizing agent and solvent for many non-metal materials. So it's rubber materials and sealant materials. Not all rubber could be used together with fluids. Instead, to test it, and only certified rubber can be used. So it means with rubber materials may be more expensive, but it finally gives fire safety. And second, it's a little bit toxic. Below you can see different names, designations of foreign hydraulic fluids. With Skydrow, it's and with MIL H83-32, it's analog of NGZ, so it's also non-flammable. Hijet 4 and MIL H5606, it's just analog of petroleum-based AMG10, so it's also flammable. And now let's take a look to the table. Here you see 4 with fluids and their parameters. Appearance. I said about colorant. AMG10 has a red colorant, so it's easy to distinguish by the leakage of the red liquid that clear it is a hydraulic fluid. 750C3 has yellow colorant, and NGZ has violet blue, which simplifies with designation. Kinematic viscosity variation with temperature. You see how much it is changes. At low negative temperature for aviation, minus 60 is limiting temperature. You see it's huge figures, 1,250, 4,200, 3,900. But at plus 50, you see some units, 10, 8.7, so kinematic viscosity changes in 1,000 times practically. And 2,000 degrees, it's only with fluid can withstand with temperature. Some kind of temperatures. Temperature of self-ignition. So it's temperature at which a fluid can self-ignite without something extra. So you see that for with non-flammable fluids, this temperature exists, but it is rather high. So in case of real fire, of course, it will be fired. But in other cases, it will not be fired. Flash point, when a flame is applied, it's possible ignition. Значит, for AMG10 it's rather low, 93, for with 753 it's rather high, 200, and for NGG it's lower a little bit, but higher than this, about 150. And freeze point, so negative temperature at which it loses mobility, about -70, here -65. So it's just suitable for aviation temperature interval. Well, of course, this figure we desire to have higher, but it makes fluid more expensive. Working temperature interval, so it's actual temperature interval within which the fluid is certified for application. As you see, -60 plus 55, it's of course very narrow. Plus 55 for hydraulic fluid, which is heated during operation, it's not enough. Here you see the best, -60 plus 175, and short term up to 200. Here a little bit lower, but also suitable, -55 plus 150 for civil aviation, it's suitable. But of course, we desire to increase this figure. Working pressure for all of this fluid is 21 megapascal. In domestic practice, I didn't know about 35 megapascal application, but for 28 megapascal, the same fluids are used, I see. Sukhoi 27 has 28 megapascal and uses AMG10. Acid number, it's a quantity of kali OH over gram to make it neutral. So there are more, with figures, there are more chemically active fluid is. As you see, AMG10 is the best from this point of view. All other synthetic fluids are more chemically active. Well, as is, feature of chemistry. And its density. As you see, AMG10 has density like a heavy kerosene. Practically by content, it's very close to kerosene. But with synthetic fluids are heavier and heavier than water, as you see them, and they have quite complicated chemical composition. Well, that's all with fluids. Let's now discuss features of hydraulic systems of modern aircraft. Let's begin from schematic features. And we will discuss separately supersonic maneuverable aircraft, so fighters, attack aircraft, next passenger transport aircraft, and helicopters, because some of them has own features. First of all, it's possible to mention that any hydraulic actuator, also its device which control flight control surface or something else, can be connected to the hydraulic system in 3 different ways. And this picture illustrates for you with 3 different ways. First, simultaneous drive connection into 2 independent working hydraulic systems. Here critical word is independent and working. So such type of connection can be called duplication or parallel redundancy or passive redundancy or constant redundancy. So it means both hydraulic systems normally supplied to flight control actuator and both working together in parallel. So it's the best, but it's the heaviest and the most complicated. So in case of any one hydraulic system pressure drop or leakage, the actuator continues to perform all its function only with twice less speed, because enough pressure will be provided, but total power is decreased, so with the same force will be decreased speed. Second type, so it's possible to say that from this point of view, first type of connection is the most reliable and desirable, but the most complicated and the heaviest. Second, drive switching. from main to emergency power system, or standby, or series, or active redundancy. So what does it mean? You have only one chamber of the actuator, and you have normally one hydraulic system attached to the actuator. But second standby hydraulic system can be switched to the actuator in case of pressure drop in the first one. What's possible to say? From point of view of mass, complexity is usually more simple and lighter than first one. From point of view of reliability, it's a question. It depends on the switching device. If switching device is reliable enough, it's comparable reliability with the first structure. But if switching device can fail by itself, in this case, we can lose actuator with both hydraulic system working. So it's worse case. In domestic literature, they say that the first is the most reliable. But now you will see, not now, next time, you will see that second type of actuator connection, it's also very useful. And the third type of connection, when actuator is attached only to one hydraulic system. Quite clear that in case of this hydraulic system failure, this actuator becomes inoperable. So it's impossible to control this control surface by this actuator. But it's possible to use another actuator for the same control surface. Well, some general remarks which is possible to mention here. When we say about independent hydraulic system, we should look for critical points. Critical points, it's such a points of hydraulic system which failure can destroy, can damage more than one hydraulic system. The most clear example is a hydraulic tank or reservoir. In the past, it's possible to see that we have two hydraulic systems, but they have one common hydraulic tank. So quite clear, if there is a leakage in the tank, we will lose both hydraulic systems. So this system is impossible to call independent. Two hydraulic systems, but they are non-independent, so it's bad. In modern wood, you will not see non-independent hydraulic system. Almost all of them independent just to this reason. But sometimes maybe in a situation, for example, this switching device is attached to both hydraulic systems. And in case of failure of this or mechanical destruction of this switching device, we also can have leakage from both hydraulic systems. So it's also a critical point. Next, it's possible to mention that subsonic maneuverable aircraft usually have 2 or 3 independent hydraulic systems. In case we have control system actuators only, ailerons, elevators, rudders, and that's all. Another hand, it is called usually power control or flight control hydraulic system. And another system is usually called booster or another system usually called combined primary or main, which will supply second chamber of flight control actuators. What you see, second chamber, first chamber with a second chamber, and all other consumers. No, it means landing gear, flaps, slots, etc., secondary control system. In case of free systems application, we usually have 2 independent hydraulic systems for flight controls, and the third one, which is called utility or auxiliary, supplies all other consumers, such as landing gear, flaps, slots, etc. So such usually have higher weight, greater weight, and greater complexity, and is used in more heavy airplanes. It's possible also to mention such feature as cutoff wells of flow limiters. When we have complicated, expensive hydraulic system, we can subdivide it to 2 or more branches or loops. And one loop is more critical, another loop may be less critical. First loop will supply flight control system actuators, maybe something else. Another loop will supply not so critical devices. And with cutoff valve or flow limiter can terminate fluid supply to these secondary consumers in case of pressure drop in the system, fluid quantity lowering in the tank, or a command from the pilot. So in this case, we conservate, we keep remaining fluid only for flight control system actuators or the most critical actuators. So it's a method of localization of leakages. So it's possible to say that all the consumers can be subdivided to three groups, first, second, and third, depending on criticality, depending on consequences of failure of the actuator. So in case of crash is a result of failure, we usually call it first group of consumer, and we usually use duplication. So like this. For second group of consumers, result it's emergency. And just for these devices, we use switching. And third group of consumer, non-critical, in this case it's mission failure. So in this case it's enough to connect actuator to only one hydraulic system. We see general ideas. Here you see examples which actuators can relate to different groups. You will see this on examples in our first lab work. I suppose quarantine will finish in some weeks, and I suppose we will have lab works normally without remote classes. So in this case, we will see what consumers. I'm sorry, peculiar, please. Do you hear me now? Here, okay. Next, as for heavy aircraft, so it means passenger transport and other. The majority of these aircraft has 3 or 4 independent hydraulic systems. Some of them has 2, but it is very specific. And of course, systems must be independent. Systems reserving is provided by duplication and standby types. So both versions are used, but has some features. In military aviation, usually they use this tandem type actuator. So one actuator connected to 2 hydraulic systems. In civil aviation, it's exception, as the most often they use this third type of connection, but for the same control surface, we will connect some actuators attached to different hydraulic systems. So in this case, all is reserved. Rods, cylinders, attachment links, and hydraulic systems. Mass is greater, but reliability is greater also, and survivability. It's possible to mention that a lot of other solutions are used in heavy aircraft to increase reliability of the system as a whole. I mean not hydraulic system, I mean some system which we control. For example, landing gear system. Landing gear should be retracted and next extended. No, retraction usually don't require special redundancy. If landing gear not retracted, you will make immediate landing. It's not a problem. Problem is how to extend landing gear in case hydraulic system failed, which normally extend it. Which is why for such heavy aircraft it's possible to see situations when, for example, wing legs are extended by one hydraulic system, but body legs, if they are, by another hydraulic system, but symmetrical. In case of landing gear extension, we usually select extension direction so that ram flow will help landing gear to be extended and to be fixed by downlocks. So all this simplifies for the flight crew, counteraction to the emergency in these conditions. And finally, maybe mechanical or electrical extension system as a standby one. It's possible also to mention that in the heavy aircraft, You usually have some sections of control surfaces, 2 or 3 sections of elevator per one wing, two or three sections of aileron per one wing, 2 sections of elevator for one horizontal stabilizer, 2 sections of rudder. And of course, each section will have not one, but 2, 3, or even 4 hydraulic actuators attached to different hydraulic systems. And of course, it will be independent hydraulic systems. And one more feature is application of self-contained hydraulic drive, just for primary flight control system devices, as for aileron, rudder, and elevator. What is this self-contained drive? It is one unit which includes hydraulic reservoir, so tank, hydraulic actuator, and hydraulic pump actuated by electric motor. What's the benefit? Benefit is termination of leakages. So self-contained drive will be located just near to object of actuation. So near to aileron, near to elevator, near to rudder. And no hydraulic lines, no long hydraulic lines passes through the aircraft. Electrical lines passes. You can say, what's the difference? We just discussed it in previous lecture. In case of electrical line broken, no leakage of electricity. You can have another electrical line connected to the same device by another way, which is not broken, and it will supply all the function with power. But if it is hydraulic line broken, it will be leakage, and all the fluid from the system can be lost if we don't use special shut-off valves, etc., etc., etc. So self-contained drives now are used rather widely as emergency devices, and I think in future almost all hydraulic systems will use just with self-contained drive. Features of helicopters. Helicopters' primary feature it's power supply to hydraulic system. As opposite to airplanes, when power is taken from each engine, or almost all engine, helicopters never connect hydraulic pumps, to engines. They connect pumps to main reduction gearbox. What's the difference and why? Difference is very simple. In case all engines flamed out or stopped, helicopter will return to auto rotation mode, and in this condition, flow speed from the vertical descent of helicopter will rotate main rotor. In this case, it's possible to deflate helicopter and to provide safe landing, but in the same time, when main rotor is rotating from out rotation, it will rotate main reduction gearbox. Pay attention, it's vice versa. In normal state, reduction gearbox rotate main rotor. But in the out rotation mode, main rotor will rotate reduction gearbox. And in any case, reduction gearbox is rotated. So all the pumps which are connected to reduction gearbox will also be rotated, will be driven by ram pressure. And so all the hydraulic system also will work. Not maybe with low pressure, but it's usually enough to provide controllability of helicopters. This is main feature. As a result, practically helicopters don't use more than double redundancy, because hydraulic system failure, it means leakage only, nothing else. If main reduction gearbox have failed, it's a crash. Here, nothing help. And it's also possible that variable delivery pumps are used as primary devices both for heavy aircraft, for subsonic aircraft, and for helicopters. Well, let's now turn to hydraulic system type features. And also we discuss it in different manner. Так, что-то тут. Some guys attach, some guys detach. Supersonic maneuverable aircraft. They widely use independent closed-type hydraulic systems. We discover why it's independent, you understand. Now almost all hydraulic systems are independent. closed type we discuss benefits, and just in maneuverable aircraft it's the most required, so it is used very widely. In such systems, overpressure at pump inlet is created by high-pressure gas or working fluid acting on the floating baffle in the special structure hydraulic tank. This tank you will see a little bit later when we will discuss components. But main idea, with baffle, like a piston in the hydraulic accumulator or fuel accumulator, will separate air chamber from fluid chamber, and so prevents air from dissolving in the fluid. Closed-type hydraulic system provides the following advantages. First of all, overpressure at pump inlet is provided under any aircraft attitude and long-term acceleration, including negative and near to zero. Pay attention for such maneuverable aircraft. It's quite normal to have near to zero or negative acceleration, which is why for them it is critical. Better fluid operating condition because of low salt air content. As a result, we have maybe special air separators, and it increases allowable temperature. What does it mean? Cavitation. Cavitation will be defined by temperature and gas content. If we decrease gas content, so cavitation will take place at higher temperature or at lower pressure. So it's both is good. It allows to operate at high altitude without cavitation with higher temperature subsonic aircraft, high temperature because of air stagnation temperature. Stiffness of the system actuator control surface is increased. We discussed today that when we have gas dissolved in the fluid, fluid becomes compressible. If we decrease content of the dissolved gas, we increase stiffness of the control surface and hydraulic actuator to gas. Working fluid cleaning improves because less volume of the fluid is required in the hydraulic system. So in this case, we don't need special engine to operate at near to zero or negative acceleration. As disadvantage, it's possible to mention that such tank, closed-type tank, becomes far more complicated and a little bit heavier. As for heavy aircraft, in the past, they almost everywhere use open-type hydraulic systems because it is more simple, and for subsonic passenger and cargo aircraft, it was quite suitable. Near to zero and negative acceleration should not be, especially long time. Pressurization provided by air from engine compressor, so it's easy. One important advantage of this open-type hydraulic system is the following. It is easy to provide uncompensated fluid volume. What does it mean? Imagine you have in hydraulic systems some very powerful consumers. Usually it's landing gear actuators, which must extend or retract landing gear. So depending on with actuators position, so landing gear extended or retracted, volume which can be inside actuators or next can be removed to hydraulic tank can vary substantially because it is powerful, so it's big volume. And as a result, a hydraulic tank must compensate this big volume difference. So in open-type hydraulic system, it is very easy. But in closed-type systems, we need to foresee some features for this purpose. Semi-closed type hydraulic systems were used in supersonic aircraft such as Concorde, when nitrogen was used for pressurization instead of air, when flammable hydraulic fluids are used. When aviation turns to non-flammable hydraulic fluids, I said that this problem was removed and now they are not used. Helicopters can use both open and closed type hydraulic systems. Hydraulic system main power sources. It's possible again to subdivide this problem for subsonic maneuverable aircraft and for other aircraft. That I just mentioned that practically all airplanes use as a primary or main power sources for energy hydraulic pumps connected directly to engines, not actually to engine accessory gearbox. These pumps usually a variable delivery, so it simplifies its operation but makes the structure of the pump a little bit more complicated. This table shows you real examples and schemes of possible versions of hydraulic systems power supply in the maneuverable aircraft. Now, it's possible to say that there are single-engine aircraft. Now, it's possible to say there are in modern wood single-engined military aircraft. It's something rather seldom. Twin-engined aircraft more often, but something light may be used, especially Chinese, maybe single-engine. And we discussed previously that it can be two independent hydraulic systems or three systems, also independent. This picture shows you engine and mechanically driven variable delivery hydraulic pumps. In the simplest case, one engine can operate flight control system and combined system. No, small remark. For hydraulically assisted control system of the aircraft, we never will have one hydraulic system. Because if in case of one system failed, it's a crash, immediate crash. And pilots have no ways how to counteract it. So minimal number of control systems is two. Hydraulic systems is two. Less than two, it's possible only in case you have an assisted flight control system. When muscle force of the pilot is enough, you may have no hydraulic system at all. Some light piston engine aircraft can fly without hydraulic system. If landing gear not retracted, what for do you need hydraulic system? A pneumatic system can be used for flaps, for example. So in modern wood, as minimum two hydraulic systems you have. We discussed it. One of them is flight controls, only for primary flight control systems, and another is combined for second chamber of flight control system and for all auxiliary devices, flaps, landing gear, slots, etc., etc., etc. In the list below, you see airplanes which are equipped by this scheme, and here there are some designations. Underlining means open type hydraulic system. A box means closed type hydraulic system. No, I said semi-enclosed, it is very seldom. Nothing, it means no information was available when I wrote this synopsis. It is also possible to see three independent hydraulic systems in single-engine aircraft, but it is a big rarity. Two American airplanes are examples. F-100 has all three hydraulic systems driven directly from engine. F-105 has utility system driven by electric motor. Maybe, but final electric motor is also driven from electric generator from engine. So it's a little bit different, but very close. So it's possible to say majority of single-engine aircraft has only two hydraulic systems. For twin-engine aircraft, here far more variety than in previous case. The simplest condition from point of view of our opinion about reliability is shown in this picture. There are two engines. Each engine is mechanically connected and drives two pumps. One pump from flight control system and one pump from combined system. And here the same. It seems it is the best condition in case of any one engine mechanical failure. Both systems will continue to operate. And the solution was used in the past for some attack aircraft, for some fighters. But experience shows it is not the best. Why? In case of engine fire, it's possible to get in a situation when both systems will have leakages near to the fired engine. And both systems can be lost in case of one engine have problem. So second picture, which looks like less reliable, may be comparable or even more reliable than previous. So here, each engine rotates pump of only one hydraulic system. And in case of one engine failed, we lost one system. But another system, it's possible to guarantee will not be lost. I'll listen a bell, so let's have a break. And I will call the roll. Так, вот we are... О, господи. Так, Alan Paul. Yes, I see. David Daniel Titus. Vanitha. And Peculiar. So, Bela Shekai Sebastian absent, Egunika absent, Maduike absent, Ravi Chandran absent, and Syed Zahir Abbas absent. Блин, не в то место отметил. Well, I also listenable, so we should continue. Значит, we discuss with second picture for twin-engine aircraft. You see such aircraft as A-10, so it's American attack aircraft, very reliable, very survivable. FA-18, also it's fighter attack aircraft. Jaguar and Tornado, European military aircraft, and Sukhoi 27. And all of them use this system because experience shows that it's more survivable in case of engine fire. It's for exception, it's possible to mention Mikoyan 29, which has two engines connected to accessory gearbox, common accessory gearbox, and from accessory gearbox we have connections to the pumps of both hydraulic systems. So in case of any one engine failed, both hydraulic systems will work, and it's mechanical connection. So because they are a little bit separated, so direct fire will not damage hydraulic systems. But you can mention that this accessory gearbox is a critical point, critical unit. In case accessory gearbox will fail, of course both hydraulic systems will fail. Yes, I agree, but mechanical arrangement of this accessory gearbox between engines make it failure by external actions low probable. In this case, first of all, engines must be destroyed. And it's possible to mention that Mikoyan 29 is very light aircraft, so its reliability, of course, can be limited. It could not be very high. As for free twin-engine aircraft, having free independent hydraulic systems. So usually they are more heavy aircraft, and the most common it is this system, when each engine has a hydraulic pump for flight control system, each flight control system, first or second, and each engine has another pump for utility hydraulic system, so which provides auxiliary function. Such airplanes as F4 Phantom 2, F-15 Eagle, YF-23 Black Widow 2 use this system. So it's rather heavy and more expensive aircraft. F-14 Tomcat has non-symmetrical structure. One flight control system attached to engine number one, but engine number two rotates combined system. It looks like this structure. But there is one more flight control system driven by electric motor, driven hydraulic pump. Non-symmetrical, but also reliable structure. And it's possible to mention with small remarks that if we have free hydraulic systems for two engines, total mass of hydraulic system will be approximately 1.2 to 1.5 times greater than in case of two independent hydraulic systems. So reliability increases and mass is also increased. As for heavy aircraft, it's possible to say that here the same features of connection. Hydraulic pumps are attached directly to engine accessory gearbox, to all or to some of them. And in addition, of course, there are some auxiliary pumps, but it will be usually electrically driven pumps. And now let's take a look to this table, which shows a statistic of possible versions of hydraulic system supply. For passenger and transport aircraft, it's possible to see twin-engine aircraft, three-engine aircraft, and four-engine aircraft. Well, three-engine aircraft, it's now exceptions, not so many aircraft, mainly twin, jet, and four-engine. Number of hydraulic systems can be 2, 3, and even 4. More than 4 in the aircraft I didn't see. Maybe it's in some exceptions. So let's discuss with schemes. It's possible to say one general idea. If number of hydraulic systems is equal to number of engines, it means with diagonal. In this case, it's clear. The lighter airplane, the less number of systems. The heavy airplane, usually for engined airplanes, are heavy. The more mass and effort designers apply for reliability increase. So diagonal is clear. And first of all, for us, interesting a deviation from this diagonal. Why designers apply more hydraulic systems than number of engines, or why they apply less hydraulic systems than number of engines? Once again, I'd like to mention this first box. Here you see first version, but without examples. In theory, such connection of hydraulic systems to each engine of two is possible, but I never see it in reality because of this problem which I mentioned before. In case of one engine fire, both hydraulic systems can be damaged, can be leaked, and can be lost. This is more often connection when one hydraulic system is attached only to the own engine. Here you see gray connection, cross-feed valve. It's a method one of the methods, the version method, how to transfer hydraulic power from one hydraulic system to another hydraulic system. But such method is the version due to one reason. It makes the systems non-independent. In case this valve is closed, the systems are independent. But in case, for example, one engine has failed, engine number one failed, and we wish to supply hydraulic system number one from engine number two, we open this valve. All is okay until no leakage in the first system. But if it was a fire on the engine and system number one was leaked, and we open the shut-off valve, we can leakage from second system and lose control, and it will be a crash. Which is why this method, cross-feed valve, is used extremely seldom. As I remember, it's Antonov 134 or Antonov 74, one of these airplanes. So difficult to say it's good solution. Well, let's now discuss deviation from diagonal. When a number of hydraulic systems is greater than number of engines with boxes, three systems for twin-engined aircraft, it's direct desire to increase reliability or survivability, nevertheless mass expenses. So it is used very widely. You see almost all Boeings and Airbuses, twin jets, use this solution. Airbus 310, 320, 330, I don't have information about 300 at that time when I make this synopsis. And 350 again at that time when I make this synopsis. Boeing 73, 5, 6, 7, and 87. Russian regional jet, Tupolev 204, Beriev 200. But here there is small difference. In Tupolev and some Airbuses, one hydraulic system is driven by left engine, one by right engine, and middle system is driven by both engines. So the same problem. In case of one engine fire, it's possible to have two hydraulic systems lost. And second solution, which is applied exclusively in the Boeings and in some other airplanes, middle hydraulic system doesn't connect it to any one engine. So in case of both engine fire, we could not lose hydraulic fluid from this middle hydraulic system, as opposite to previous case. What are the power sources for this system? It's only emergency power sources, electric motor, and maybe a ram air turbine. We will come back to this ram air turbine a little bit later and we will discuss emergency power sources. But it is used almost everywhere in civil aviation. For hydraulic systems in a twin-engined airplane, it's exception. I don't know any one civil airplane for this with this scheme. It's SR-71. It's American Strategic Reconnaissance. Two flight control hydraulic systems and two utility hydraulic systems are on these airplanes. Totally, there are four. So it's exception, and it's a little bit another situation. situation when there are three engines and four hydraulic systems, we can imagine in theory, but again, I could not give any one example of this real implementation, no, because three-engine airplanes now assumed not effective. There are two-engine or four-engine airplanes. Now let's discuss deviation upwards when number of hydraulic system is less than number of engines. Middle box, this box shows you three engine airplanes with two hydraulic systems. Yakovlev 40, Yakovlev 42, and you see it's non-symmetrical structure. Explanation is very easy. These airplanes have manual flight control system, so manual reverse flight control system. Hydraulic systems are not used for flight control. So both hydraulic system failure will not result into immediate crash. Airplane is normally flown by pilot muscle force. So hydraulic system is used only for utility purposes, landing gear, flaps, etc. So they are not so critical. Really, Antonov 148, Ilyushin 114, MD-80, Bak 111, the same. It's rather light airplanes which doesn't need hydraulic system for flight control. Very interesting with right top box. When we have four-engine airplane with only two hydraulic systems. And here it may be two different answers. By 146, it's right airplane. It's unclear for me what for they need four engines for this airplane, but they have. And it is manually reverse flight control system. So hydraulic systems are only for utility purposes, and so its failure doesn't result to crash. Landing gear you can extend by another method. But Airbus 380, Ilyushin 76, Boeing 50, B-58, they have interesting solution. In addition to centralized hydraulic system in Airbus 380, or in addition to auxiliary centralized hydraulic system in Ilyushin 76, they have a lot of self-contained drives. It's hydraulic system which is very small and localized. It has own tank, own electric motor driven pump, and one actuator for all flight control system actuators. So ailerons, rudders, elevators can be controlled in case of both centralized hydraulic system have failed, which is why two hydraulic system is enough. C-135, what it's interesting to ask you, do you know what is C-135? It's a cargo version of Boeing 707. Very famous airplane, not actually vice versa. Boeing 707, it's a passenger version of C-135, not one. So it's an airplane which was flown by the pilot with muscle force, but it is rather big airplane, via servo taps. So pilot could not move directly elevator, rudder, aileron. It's huge forces required. But pilot deflect servo tap, and servo tap deflected aileron, elevator, or rudder. So it's a very good idea, and in some heavy airplanes, this solution was used. For example, Antonov 22. But in Antonov 22, it is used as emergency. Here, it is used as normal flight control. So this solution now is assumed advanced Airbus 380 due to decrease of mass. And this box shows us two European airplanes, Airbus 340 and Concorde, which also have four engines but three hydraulic systems. So idea is a little bit different. Airbus use almost everywhere three hydraulic systems. independently of number of engines. So I suppose they have calculations, mathematical calculations, which was shown that free hydraulic system is enough to fly above the ocean for a long time. It doesn't matter how many engines, and they use the same pattern for the hydraulic system designing independently of engine number. So it simplifies designing of hydraulic system for different airplanes. For example, what's the difference between Airbus 340 and Airbus 330? Mainly in engine number. Its wing structure, its fuel system are very similar, with very small difference. So hydraulic system also rather similar. Well, that's enough about this. As for overpressure, I said that all modern airplanes use 21 megapascal overpressure, C-17 28 megapascal, and the most modern Airbus 380 and Boeing 787 35 megapascal. As for helicopters, but it's possible to say that helicopters are not so complicated by not so vary in the structure of hydraulic system supply. The general idea is, principal idea is, we take power from main reduction gearbox. So there are engines which rotate main reduction gearbox, but from main reduction gearbox we have pumps which supply power to various systems. Picture number 1 shows classic structure, the simplest structure for designer, but not the best. Principal difference of picture B, when in the reduction gearbox there is separate connection for another pump. So in case of one structure is damaged, one other shaft, it's small extra mass, but it provides extra reliability. Picture C shows us how it's possible to simplify ground maintenance operations for helicopter. Pay attention, if you need to inspect operation of hydraulic systems at ground in first and second case, and in the case D or E, you need to rotate main reduction gearbox. So it's impossible by another method to check hydraulic systems operability. But picture C shows that you can use APU and separate reduction gearbox. Here maybe mechanical coupling, overrunning clutch, for example. APU will rotate with additional gearbox, intermediate gearbox, and it will rotate some hydraulic system. So main reduction gearbox can be fixed in this case. Main rotor can be folded, for example, for carrier-based operation or for some other situations when rotation of main rotor can be dangerous at ground or is prohibited. So this is a little bit more heavy struct solution, but it allows to improve operational convenience for the ground maintenance personnel. You can also see here this structure. It's a hydraulic accumulator and a pure start hydraulic system. So I should mention that we will not discuss starting systems. It's a component of power plant lecture course, team 12. Fourth part of synopsis. Due to lack of time, it is also for independent study. But it is discussed there that hydraulic system can be used for starting. So usually it is independent hydraulic system with only one purpose, to start APU or main engines. But otherwise it can be component of centralized hydraulic system. Here you see that it is hydraulically started hydraulical system for APU start. So source for this hydraulic system operation, it's hydraulic accumulator. Next, it will rotate the APU. APU will be started, and next from APU you can bleed air for main engines pneumatic start. So this is rather widely used, especially in United States helicopters. Well, picture D shows a unique structure, four-engine helicopter with three reduction gearboxes with four hydraulic systems. It is MiG-12. It's a very specific structure, and because it's very heavy, they think how to make it more reliable and equipped it with six hydraulic systems. Well, it's unique structure. And picture E shows used pressure from power from one hydraulic pump and from another hydraulic pump can be switched from one hydraulic system to another in case of partial failures. So it's a method how to increase reliability of hydraulic system as a whole operation specific for helicopter. Well, that's enough about primary power sources for helicopters. And now let's turn to emergency power sources, which can also be used in aircraft. Here it's possible also to subdivide all this chapter to different kind of aircraft, and we start from supersonic maneuverable aircraft. As for emergency power source, we always use standby hydraulic pump. And only question is, what is the power drive for this standby hydraulic pump? Here there is a big variety. What we can use what kind of energy we can use on board the aircraft to drive this pump. The simplest but not the best is a direct current electric motor application. So such structure it's possible to use with low power. Why? Because you need a very powerful electric accumulator to rotate this motor. You understand that when we say direct current electric motor, it means it will be rotated from electric battery, and it means main engine we assume have failed. Such solution was applied in Mikoyan 21 when really there is accumulator, electric battery, and direct current electric driven motor which rotate with standby hydraulic pump. Mikoyan 21 is rather small airplane, and for such airplane maybe it's quite possible. If you have more than one engine, in this case maybe electric drive can be useful, but it is not principle for military aviation. The most often they use another solution, which is shown in these pictures. Ram air turbine. This solution I consider so detailed because it is also used in civil aviation, both passenger and transport. What is this? Ram air turbine. It's a special turbine rotated by ram air and extended in the open air when necessary, usually in case of hydraulic system or main engine failure. And it is mechanically connected to hydraulic pump and usually to electric generator to provide emergency power supply for hydraulic system and for electrical system. Usually it is attached only to one hydraulic system, which is assumed the most critical. Structures of this ram air turbine are a little bit different, but main idea is similar. Here you see 4-blade turbine from A7, attack aircraft of United States. Here you see 8-blade ram air turbine from F-02 American fighter, and here you see 2-blade structure from KC-10. It's extender flying tanker, so it is DC-10 military version. So any of them are extended by hydraulic or pneumatic or spring cylinder, and in domestic practice it's only possible to extend with ram air turbine in flight in case of emergency. But retraction is possible only at ground. It is done especially to exclude situation when ram air turbine will be accidentally retracted in flight and you could not next extend it again because you don't have power. But in American practice, they allow to extend and to retract it in flight, so they are sure that accidental retraction will not result to the failure. So, you can ask me how to extend with RAM air turbine from hydraulic system if hydraulic system have failed. Usually they have special features for the circuits. First of all, it may be a hydraulic accumulator intended only for one function. So it will be a separate self-contained subsystem which is intended only for extension of RAM air turbine in the direct airflow. And this hydraulic accumulator will be continuously recharged from engine-driven pumps. And in case engine have failed, now in this picture we have single-engine aircraft. In case one engine failure, all hydraulic systems, no matter how many hydraulic systems you have, 2 or 3, will be failed. So in this case, hydraulic accumulator is used for this actuator, which extends hydraulic RAM air turbine in the airflow, and one of the hydraulic system next will get power from this RAM air turbine and so provide all required actions. It's possible to say that here it is not so easy in operation. So this RAM air turbine must have proper turbine pitch angle control, so to keep almost constant power on the pump independently of flight speed and altitude. With altitude air density changes, and so power changes. With flight speed also power changes. So it's interesting structure, of course, not so simple, and its actual power, of course, this system tried to support power on the drive constant, but it's not always possible. At landing, for example, nobody will take off with failed engines. But at landing, when airspeed is very low, really power of this RAM air turbine will drop. And in this case, it's preferable to decrease speed of motion, but not to decrease forces, because forces can be rather big. So here you see examples of RAM air turbine installed in military aviation, but this picture shows you RAM air turbine installed in passenger airplane Aviation 96 in both positions, retracted top position and extended bottom position. In this case, you can see pivot and fixed structure. You can see movable part. You can see extension actuator. In this case, it's spring. So the most reliable, they assume it's mechanical spring. It doesn't relate from accumulator, from something from high pressure bottle. For the gas mechanical spring, they assume more reliable. A damper, which must prevent shock loading in the beginning and in the end of travel. Lock, mechanical lock and link, which fixes the RAM air turbine in the retracted position normally. Actuator, which must open this up lock, and limit switch, which shows that it is extended proper. So this limit switch also removes the brake. Here inside there is a brake which must stop with RAM air turbine from rotation until full extension. What does it mean? Imagine situation: you open the door with rod 14 used to open the door, and you begin to extend this rod. And when it extends to the flow, RAM air flow begin to press to the blades. And if blades will not be stopped in this condition, they will be directly damaged by the contact with bay of RAM air turbine. Only when it is completely extended, this limit switch will stop with brake, and only after this RAM air turbine begin to rotate and create power for hydraulic system and for electric system. This picture shows you the same RAM air turbine, but shown in axonometrical view, so that you see all the features, how they are arranged. It's possible to say why only 2 blades are used more widely in modern wood: to minimize sizes of this device in the retracted position. So it's very easy. This device is emergency device. All the flight, all the ground operation, it only extra mass and extra volume. So the less size of this device will be, the less expenses you have for this luxury installation. It is not all which is possible to imagine. Power drive connected to aircraft accessory gearbox, driven from both engines and turbine starter, can also be used. No, we discussed it in the Mikoyan 29 solution. Next, standby hydraulic pump can be driven by motive high pressure fuel. I suppose you remember from previous semester that in fuel systems, sometimes we have multi-fuel subsystem, which is used to operate, to motivate jet pumps, or sometimes even hydraulic motor-driven pumps. But as a fluid, we have fuel. So there are multi-fuel pumps attached mechanically to engines, and if engine is working, rotating these pumps, you have multi-fuel. And of course, if you have fuel on board, you have this high-pressure multi-fuel. So in some cases, it's possible to use this multi-fuel to create power for hydraulic pumps operation. In Mikoyan 29 and in Tupolev 144, maybe it's exception, but they apply this solution. One more solution, it's main engine windmilling application. Mikoyan 27, which we will discuss actually in our lab work, will apply this solution. What does it mean? It has only one engine, and when this engine is normally operating, it's enough to operate both hydraulic pumps of each hydraulic pump, one of each hydraulic system. But in case this engine was flamed out, or the fuel was consumed, but no jamming of engine. So when fuel is consumed, no fuel on board, no flame, air intake gets fresh air into engine, and engine will be rotated by this air passing via engine duct. This windmilling speed will be lower than speed in normal condition. Not quite clear because another power. And in normal condition, this power is not enough to rotate pumps. But in Mikoyan 27, in the accessory gearbox, they apply additional dual speed reduction gearbox, which in this condition can be switched to second mode. And in this second mode, it provides enough power to create not so big, not 21 megapascal, but about 16 megapascal overpressure in the hydraulic system, in the flight control hydraulic system, so the most critical. And it allows to rescue pilot and airplane in case of fuel was lost. And one more solution, it's emergency power unit. No, it's more exotic solution. It is used in United States fighters F-16 or Fighting Falcon or F-23 Black Widow 2. And you can see this solution in the following picture. What we see here. This is EPU, emergency power unit. Actually, inside the emergency power unit, we have a turbine which will be mechanically connected to hydraulic pump of system A. Instead of 1, 2, they use A, B, and it's F-16. And to electric generator, which provides electric power for essential bus, one of the essential bus. As power for this turbine, it's possible to use two kind of fluid. First, it's possible to use high pressure air bled from engine. So in case engine is working, F-16 is also a single engine fighter. It has only one engine and two hydraulic systems. And in case engine is working, but something happens with a steering gearbox or with both hydraulic pumps or with electrical system, electrical generators, and you need to have emergency power supply for hydraulic system. You can open the shutoff valve electrically, usually DC driven, and direct high pressure air to this turbine. Until engine will work and until engine RPM will allow, as I remember, it must be 75%, 75-80% engine RPM, EPU will rotate hydraulic pump and hydraulic pressure in system A will be enough, and electric generator will provide electric AC power. Or from AC, next you can tune it to DC. But in case with only one engine flamed out, jumped, broken, no fuel in the main tanks, you can use emergency power drive. With emergency power drive, in this case, is hydrazine fuel. What is hydrazine? It's a chemical substance which can be a little bit heated, and in this case, it is tuned from liquid state to gaseous state. So how hydrazine is supplied? No pumps. They use bottle with nitrogen and shut-off valve. Here there is a membrane and here membrane. When pilot presses emergency button to activate with emergency power unit, this valve will be open, high pressure nitrogen will be destroyed with membrane, presses to this diaphragm, and forces hydrazine via another membrane to initially decomposition chamber. In front of the turbine will be decomposition chamber. In this decomposition chamber, this fuel will be tuned from liquid state to gaseous state, or it's possible to preheat it, to ignite initially. And next, you understand, I suppose, if you have low volume filled with liquid, if you tune with liquid to gas, its density decreases and its pressure increases. So liquid tunes to gas with high pressure. So this high pressure will be directed to the same turbine, and you rotate the same pumps and electric generator. But in this case, operating time will be limited. It's about 15 minutes, 10 minutes, by storage of hydrazine on board the airplane. So what's good? No, it's absolutely independent on engine and fuel tanks, etc. It has rather small volume, doesn't create external drag, etc. What's bad? No, first of all, it's necessary to recharge, to service it sometimes. Second, it is of limited time. Ram air turbine will work until airplane is flying. All engines have failed. Until you have altitude and airspeed, a ram air turbine will work. This structure will work only within this time. And there more often you will deflect pumps or control surfaces, there less time will be used for this system operation. And one more, all kind of monopropellant, including hydrazine, are rather toxic. Hydrazine is lower toxic from all this kind of hydraulic monopropellant. But it's also toxic, and you can see that it's necessary to avoid getting on the skin surface, getting to the respiratory organs, etc. Так, there is 15:12, but I assume that we should stop here. No, well, time is allowed. Let's turn to second type of aircraft, heavy aircraft. First of all, they use both fixed delivery and variable delivery pumps as emergency power source, and as a power source may be sometimes similar devices. Electrically driven pumps. It's possible to mention that in modern wood, for passenger and transport airplanes, electric motor-driven pumps may be the most widespread type of the pump as emergency unit. So it's possible to look to Airbus 380. It has two hydraulic systems only, but each hydraulic system has 6 pumps. 2 pumps at one engine of one wing, 2 pumps at another engine of the same wing, and 2 electric motor-driven pumps. All other kind of passenger aircraft also have electric motor-driven pumps. What the feature. Why so? You see, it's very convenient for ground maintenance personnel. It allows to test hydraulic fluid to check control system operation at ground without running main engines or APU. It's enough to have electrical power supply from ground infrastructure, and you can test all electrical components and hydraulic system components also due to these pumps. So it's very convenient, so it is used very widely as a ground test and as emergency in case, for example, you have 4-engine aircraft. One engine have failed. All other 3 engines give electrical power. So you can supply the electric power to operate with electric motor-driven pumps in the first hydraulic system. In another case, you have 2 engine aircraft. You fly above the ocean. One engine have failed. In this condition, according to ETOPS requirement, extended clean engine operation, you must have secondary source of power. It's APU. And this APU must operate 15 hours continuously. So APU will be started and will supply electric power via electric generator. The electric power will be supplied to hydraulic pump, electric motor-driven hydraulic pump, and all the hydraulic system must work from APU until fuel is available. So it's emergency power drive, which is very widely used in modern war. Next, air turbine-driven pumps. This picture shows you what's with. On board all modern airplanes, you will have pneumatic system. Pneumatic system, it's air bleeding. Pneumatic system bleeds air from each engine and supplies it with required pressure, with required temperature to consumers. With consumers, it's environmental control system. It may be ice protection system, maybe pressurization system for fuel tank, for water tank, for water tank, for hydraulic tank, etc. But it may be pneumatic starting system for engines, it's etc. But one of the function, it may be a pneumatic motor operation. Pneumatic motor can be mechanically connected to standby hydraulic pump of each system, but it can be supplied with air from another engines. Of course, here must be check valves as minimum. Really, it will be shut-off valves, some other devices for temperature and pressure control, minimally check valve. What imagine situation? Engine number 4 have failed. So no pressure supply here and no pressure supply to its hydraulic system. We bleed air from all other 3 engines, supply it with pneumatic motor. This pneumatic motor rotates hydraulic pump in the number 4 hydraulic system, and fantastic, hydraulic system number 4 is also working without engine. So energy is redistributed from existing engine, working engine, to hydraulic system of failed engine. But pay attention, in both these cases, in case of leakage from the hydraulic system, or hydraulic system number 4 was failed due to leakage. No matter engine fire, why leakage? In this case, no leakage will be from another hydraulic systems because it will be air supplied to this pneumatic motor, it will rotate with hydraulic pump, no fluid, no. Hydraulic system number 4 will not work. But hydraulic systems all other will not fail, so they are independent. If electrical system works, the same situation. Next, ram air turbine driven pumps. So it's the most widespread for a real emergency in case fuel is consumed or engines failed. So we discussed it, I think, enough. Hand driven pump. It seems it's something obsolete, something very old. It only seems so. Hand-driven pumps are used not only in older planes, but in the most modern airplanes such as Airbus 380, Airbus 350. It doesn't mention here because when I wrote the synopsis, I didn't know about this. Now I can say. As ground devices. So you have bigger plane and you need to move some components of this airplane, normally hydraulically powered. But it is at ground, at parking. You don't want to run engines because it's expensive. You even don't want to run APU because it is also expensive. No, maybe not so expensive, but also. No, you need to open cargo door, for example. But you need to open cargo door, and next, that's all. You don't need APU. What for to run it? It's expensive. So for these conditions, it's possible to use hand-driven pumps. In the following picture, you can see example of hand-driven pumps. Well, actually, it must be later, but it is shown now. So its principal scheme is not real structure. There is casing. There are two pistons, one and two. There are pair of check valves inside pistons, each piston, and there are pair of output check valves, 5 here. And there is switching valve, element number 3, with a spring. Here there is axis of rotation, and here there is a handle. Suction connection, suction cavity, and delivery connection. In normal state, you rotate with handle, reciprocate with handle, and with pumps, with pair of pistons, will create overpressure into delivery line. When overpressure exceeds limits, this sliding valve 3 moves upwards and interconnect chamber B between each other. Chamber B will be switched off from operation, and only chamber B will work. So overpressure created and delivery will decrease, but it limit loadings on the handle. So once again, such solution is very widely used in civil aviation for ground operation. I see the time is over. So that's enough for today. Thank you for attention. I suppose next time will be more students. And look for timetable. Timetable rooms also changed. No, next week will be quarantine, but when quarantine will terminate, rooms will be little bit different. And prepare questions for a course project. That's all for today. Goodbye.